In this session, we're going to talk about surface finish, but we're also going to talk about roundness and profilometry. And the reason for this is they are all very closely related. Roundness and surface finish are about the same thing. They are looking at a condition in millions. However, roundness is the same condition wrapped around a circular feature, whereas surface finish laid out flat. Also, surface finish and profilometry, which is looking at profiles of surfaces, can also be done by similar machines. So in that case, they're also tied together. So there's a variety of videos. We're going to start out with roundness, and then we're also going to get into surface finish and profilometry, and there's quite a bit to go over. So you'll learn a lot more from these videos than I can add to the book because they have the equipment and they're showing you how to use it. So let's go ahead and check it out.
Hello and welcome to this webinar from Taylor Hobson. My name is Mike Mills and I'm the Chief Metrologist at Taylor Hobson. This is one of a series of webinars covering basic form and surface texture metrology concepts relating to our products. In this webinar, we'll be examining the components of a modern roundness instrument. If you have any questions during the presentation, please type them into the question and answer panel on your screen, and I'll try to answer them at the end of the presentation. We'll start by defining roundness in this context, before looking at the main components of the stylus, the gauge, and the data acquisition system. I won't be covering the whole instrument, and in particular, I won't be covering anything to do with the drive or control systems. I'll briefly mention roundness analysis, and we'll look at the 4 different reference circles defined in the ISO standards. During the presentation, I'll be using some simplified terms and will omit qualifications that would be necessary to make the terminology strictly correct. Hopefully, this will make the presentation easier to follow. There are different methods and instruments that can be used for the measurement of roundness. I won't be dealing with those methods or instruments, and this presentation will be limited to a roundness instrument, such as those made by Taylor Hobson. Let's start with defining what is meant by the term roundness. In some areas, roundness is called circularity, being like a circle. A circle can be defined as a line of constant radius from a point, the center of the circle. Roundness is a value used to quantify errors in the circle, which must mean deviations in radial distance from the center point. So really, when we refer to roundness, we actually mean out of roundness. The value that we assign to roundness is the range of deviations in radial displacement from the center. There are many different standards that could be applied to roundness. These include international, national, and local standards. For the purpose of this presentation, we'll be considering the definitions held in international or ISO standards. There are 3 standards that we will consider. The first is ISO 1101, which is a drawing standard. This standard shows how to indicate a roundness requirement on a drawing. It also provides us with a definition of roundness, which can be summarized as the radial separation of 2 concentric circles that just enclose the feature. The parameters, terms, and definitions relating to roundness are defined in ISO 12181. This standard is in 2 parts. The second part describing the specification operators that essentially define how roundness is to be measured. The third ISO standard that is of interest to us is ISO 4291, Methods for the Assessment of Departure from Roundness, Measurement of Variations in Radius. It's this type of instrument that we're considering here, rather than any other means of assessing roundness. Now, ISO 4291 is an old standard and was originally written when roundness was commonly assessed by reference to polar charts obtained from analog instruments. A lot of that information is no longer relevant now that roundness values are calculated by digital means. But ISO 4291 is still current and remains relevant in defining instrument types and instrument errors. There are two fundamental types of roundness instrument, and these are defined by what happens to the workpiece, that is, the item being measured, during the measurement time. The two types are stationary workpiece and rotating workpiece. Each of these types has advantages and disadvantages. Stationary workpiece instruments have the advantage that the load is not carried by the spindle, and so the instruments might be easily adapted to measure heavy components. As the component is stationary during measurement, this type of instrument is ideal for measuring components that are not rotationally symmetric, for example, engine blocks. One of the key limitations of the general purpose stationary workpiece instrument is the axial reach, because the spindle is above the item being measured. If the depth of the measurement plane is significant, then some adaptation is required to extend the reach of the instrument. These days, the most common form of roundness instrument is the rotating workpiece instrument. Rotating workpiece instruments are useful when measuring components that are rotationally symmetric. In general, they have good access to external surfaces. One of their key limitations is the load capacity, as the component being measured has to be supported by the measurement spindle. Clearly, the spindle has to be rated for the maximum load capacity required, and additionally, changes in load might well impact on the measurement capability of the instrument. Here are three different roundness instruments from Taylor Hobson. On the left is the Citronic roundness instrument, which is an example of a benchtop rotating workpiece instrument. This particular instrument is fully manual, as none of the axes are motorized. Nevertheless, it's an extremely accurate instrument using a high-precision air-bearing spindle. Although not covered in this presentation, the instrument's also capable of measuring flatness and some other parameters related to flatness and roundness. In the center of this image is the Talleyrand 500 series instrument, which is a floor-standing rotating workpiece instrument with a very high degree of automation. This enables the user to create measurement programs for frequent measurements. This particular instrument also includes precision axial and radial axes, allowing several additional measurements to be made other than just roundness. On the right-hand side of the figure is the Talleyrand 450 instrument. This is an example of a stationary workpiece instrument. The instrument is again highly automated, allowing many different measurement types. Taking the example of an engine block, under program control, this instrument is able to position to each cylinder in turn and perform the required measurements. For more information on these or other roundness instruments that we make, please refer to our website at taylorhobson.com. Now, I mentioned previously that one of the limitations of the stationary workpiece type instrument was the limited reach in the axial direction. Here we see how such an instrument can be adapted to measure at a deeper extent. So here's the radial arm that rotates as the measurement is being taken. The gauge is normally attached directly to the radial arm just here, and the measurement plane would normally be about here. For a deep component such as this one here, what we've done is we've put an extension tube between the radial arm and the gauge itself, allowing the gauge to measure further away from the radial arm and giving it a much greater access. Finally, here's a different type of roundness instrument. This is a bore measurement instrument. This is a special case of a stationary workpiece instrument. This is one of our Tally series instruments, and with this instrument, the measuring head sits inside the component to be measured. The principles of measurement are the same as for other roundness instruments. It's common for these instruments to contain several different measurement points along the axis of the measuring device. They're highly specialized instruments. They work over a limited range of bore diameters and with gauge positions that are fixed in different locations along the axis. However, this type of instrument is ideal for providing rapid measurements in bores on workpieces such as cylinder blocks and can be extremely cost effective in a production environment. For the rest of this presentation, we're going to focus on the most common type of roundness instrument, the rotating workpiece instrument. In this image, the main components of the measuring system can be seen, and we'll look at some more of those in more detail in the next few slides. First of the main components is the stylus. The stylus is often interchangeable. So for example, just here, the stylus can be inserted into the stylus holder and removed, changed with a different stylus. And the stylus can often be altered in its angle in relation to the axis of the gauge, and you can see the mechanism here for doing that. The stylus force is also adjustable. Difficult to see on this image, but there is a stylus force adjustment knob just here on the side of the gauge at that point. The stylus tip is an essential element, forming the one point of contact with the surface under test. The size, shape of the material of the tip will all affect the results. Typically, the tip is a polished sphere of a suitable hard material such as ruby, silicon nitride or tungsten carbide. The diameter of the sphere is usually of the order of millimeters. The gauge, which is this part here, is responsible for converting the small movements of the stylus into an electrical signal that can be processed and recorded by the data acquisition system. Frequently, the gauge has, as I've mentioned before, some mechanism for adjusting both the stylus force and the angle at which the stylus is presented to the surface. Moving on to the spindle, this is obviously vital to the operation of this type of roundness measurement instrument. Various types of spindles are used depending on the application and the load requirements. Hydrostatic bearings use either air or oil and are very common these days. For the measurement of roundness, the spindle or spindle drive needs to provide some reference as to its position relative to a 0-degree reference point. In a rotating workpiece instrument, the spindle will typically be fitted with a centering and leveling stage to aid alignment of the component axis to the rotational axis of the spindle. The silver top on this one is the centering leveling stage. This is one of two centering knobs, and this is one of two leveling knobs that are provided. So there are some other main components which we're not going to look at in any detail. And for example, there is the arm, the column and the framework, and they provide the support to the gauge and can provide additional capabilities or features to the instrument. For example, linear axes that are motorized or provide straightness datums may increase the flexibility of the instrument or extend its capability to other measurement types such as straightness. The framework will usually incorporate some form of anti-vibration mounting to isolate the instrument from external noise such as floorborne vibration. And the electronics really contains the data acquisition system and some form of computer for reporting purposes. So once the component has been loaded for measurement, the basic approach to the measurement of roundness follows a pattern similar to the one that's outlined here. Firstly, the stylus is brought into contact with the component, and then the component is aligned to the axis of rotation. The stylus is then moved to the required feature, and the component is measured by rotating the spindle. Stylus tip deviations are recorded as a function of spindle position, and the resulting dataset is then analysed to produce the result. With an automated instrument, the entire sequence could potentially be initiated by a single touch of a button. For a manual system, a skilled operator is required to perform the alignment and then initiate the measurement sequence. An appreciation of some of the concepts of data acquisition is useful, as this might impact on the measurement settings. In a modern digital instrument, the data acquisition system is responsible for converting the analog signal into a digital signal. And this implies some form of sampling, which is usually triggered either by a timer or by some feedback of the spindle position. There might also be a need for amplification, especially where there are selectable ranges, such as in our inductive systems. However, there will almost certainly be a filtering stage. This could be an explicit filter or one that's inherent in the way in which the converter works. This graphic here shows the inductive gauge. Movement at the stylus tip will cause movement of an armature within the coils of a variable differential transformer. The electronics associated with the transformer produce a signal that is proportional to the displacement of the stylus tip. Now, for clarity, I've omitted from this diagram the stylus angle setting mechanism and the interface between the stylus and the gauge. However, what is immediately apparent is that the stylus is part of a lever mechanism. So the stylus beam here between the tip and the pivot, and then there's a beam here between the pivot and the armature. If we alter the length of the stylus beam, it alters the ratio of this lever, and that alters the range and the resolution of the instrument. The data acquisition system is responsible for initial signal conditioning. And that means for converting the individual readings into a digital format and for storing the readings for later processing. Signal conditioning might involve filtering and amplification of the signal. Different levels of amplification might be used to provide different ranges. For example, for alignment settings such as centering and leveling, or a higher amplification for measurement. It's useful to have an understanding of filtering in the data acquisition system, as it might impact on the measurement results, although this is normally only a consideration for wide bandwidth measurements. In the data acquisition system, filtering is important for two primary reasons: to reduce or suppress noise, and to ensure that the sample conditionings are met by limiting the upper frequencies admitted to the analog to digital conversion stage. If the upper frequencies are not adequately suppressed, then aliasing may occur. Now, aliasing is where a signal is sampled more slowly than necessary, resulting in the sampled signal appearing like a lower frequency signal. The frequency at which you must sample above is known as the Nyquist frequency. So this graphic shows how a sine wave that's sampled more slowly than necessary appears as a sine wave with a lower frequency. And this is aliasing. So you can see the blue sine wave there with 5 cycles, and the orange sample point shown by the circles are at longer than half of one wavelength. As a consequence, when you reconstruct the sine wave from the sampled points, you end up with the orange sine wave that's shown, which is a much lower frequency than the sine wave that was actually the original frequency. Data analysis is accomplished these days by some form of digital computer. And this might be an embedded computer, might be a PDA, such as we use on our Citronic products, or it could be a separate desktop computer, such as a PC. One of the first requirements of the analysis system is to apply a band limiting filter to the data. This deliberately modifies the recorded profile by limiting the wavelengths to prescribed values in prescribed ways. This has two benefits. Firstly, it removes wavelengths that are not considered to be relevant, and secondly, it provides comparability of the analysis from one system to another. This intentional modification of the profile alters the final result that will be derived from the profile. For this reason, it's important to make sure that the correct filter type and cutoff are selected when analysing the data. The second requirement of the data analysis system is to provide parameter results. Additional results such as graphical displays or printouts are also frequently provided. Now, ISO 12181 defines several parameters relating to roundness. However, the parameter most frequently used in roundness assessment is total roundness, sometimes called roundness peak to valley, and is designated as RON-T, as shown there. So before looking at how we might actually calculate roundness, it's instructive to remind ourselves of the definition of roundness, which is the separation of two concentric circles that just enclose the profile. The profile that we're enclosing now is the filtered profile, as discussed above. The term just enclose implies that the two circles are separated by the minimum radial distance to contain the profile. By defining roundness in this way, it raises an important question. What centre? Or put another way, how do we find the appropriate centre from the set of data points that we have recorded? We cannot simply use the zero deflection point of the gauge, as the data will be impacted by errors in the alignment between the component axis and the spindle axis of the measuring instrument. Somehow, we have to eliminate those errors from the data. So to make our results reproducible from one system to another, we need to have defined criteria to use when removing the alignment errors from the data. For this purpose, the ISO standards define 4 reference circles that can be fitted to the data. Each of these fits will normally result in a different centre and a different RON-T value. It's important to note which fit is required on the drawing and to make sure the correct reference circle is used for the analysis. So LSCI is the least squares reference circle. This is analogous to finding a best fit straight line to data in a spreadsheet. The fitting balances the data either side of the reference circle. The advantage of this type of fitting is that the fit is not easily moved by small imperfections in the data, such as might occur if there were a scratch on the surface. The minimum circumscribed circle is the smallest circle that will just enclose the data. This might be used on the external surface of a solid figure to ignore any scratches, etc. on the surface. However, this fit will be directly affected by any outward projections, such as a burr or piece of dirt. The maximum inscribed circle is the largest circle that will fit inside the data. This fit might be used on the internal surface of a bore to ignore any scratches, etc. on the surface. However, just like the MC circle, this fit will be directly affected by any inward projections, such as a burr or piece of dirt. Finally, there is the minimum zone circle, or MZCI. This fits 2 concentric circles that just enclose the data. This definition is essentially identical to the definition of roundness, and this fit will always produce the smallest RON-T value. However, like the MC and MI, this fit is directly affected by any imperfections in the data. Because the reference circle affects the definition of the centre, and therefore the RON-T value, it's important to note which reference circle is to be used. Some older drawings might not indicate the reference circle, or for that matter, the filter. These requirements should be clarified before making the measurement. In this slide, you can see the different reference circles fitted to the same data. The radial scaling is actually the same for each of the 4 plots, but as the reference circle is used to place the data within the grid, the presentations for MC and MI circles look different from the LS and MZ circles. In the MZ example, which is this one here, you can actually see 3 different circles. The intermediate circle is simply the halfway between the 2 circles that are fitted as part of the MZ reference. To illustrate the differences in centres, I've done the calculations for each of the circles, and I've set the centre of the least squares circle as the datum. This means that the centre values that are shown here are with respect to the least squared centre. You can see that for each of the reference circles, the centre values have moved, and you can see that the RON-T values have changed quite significantly. Now, the RON-T values are very small on this component. However, the fact that there are 4 very different RON-T values helps to reinforce the fact that the correct circle must be chosen in order to produce a comparable RON-T value. So in this presentation, we've looked at the 2 key types of roundness instruments and some aspects of roundness measurement, including some data acquisition considerations and data fitting. We've seen examples of rotating workpiece and stationary workpiece instruments, and we've looked at some of the advantages and disadvantages of each type. We've also looked at the definition of roundness and the 4 reference circles that can be used. We've seen how it's important to understand which filter to use and which reference circle, as both impact the results. If the choice is not clear from the drawing or other instructions, then it's important to clarify these requirements with the designer. Thank you. That brings us to the end of today's presentation. So thank you all for your time and attention, and I'll now try to answer any questions that you might have. Let's see if I can find the question and answer. So there's one here: can coordinate measuring machines which don't have a reference spindle be used for measuring roundness accurately? So I'm going to take that question apart from the last word. So let me rephrase that as: can coordinate measuring machines which don't have a reference spindle be used for measuring roundness? The answer is yes, they can, but they're not being used for measuring roundness in the way that we've described it here today. So what I've concentrated on here today is the measurement of roundness by measuring radial deviations. Coordinate measuring machines that don't have a spindle measure in a different way. They can fit the 4 reference circles to the data that has been obtained. The accuracy of the instruments is always a matter for the instrument manufacturer and the assessment of the uncertainty of the measurement that you are taking by the method you are taking. Are there any other questions? Okay, then that brings us to the end of this presentation. Thank you very much for your time and for listening, and hopefully we'll see you again at a later webinar. Thank you. Bye-bye.
Hello, today we're demonstrating the Roundness RS300 and some of the CNC capabilities. This machine has the mp4 software which will be running and managing this machine. From here we move into a part alignment. The Roundness 100 is a manual alignment, but the Roundness 200 and 300 series have automatic programmable alignment for centering and tilting with a wide range. The first thing that we will do here is we will pick a point at the lower extremity of the workpiece and one towards the top of the workpiece. As you can see on the screen here, we have an alignment box. From here we was able to choose the amount of eccentricity as a target for the alignment, so we're able to fine-tune the amount of alignment that we want. This machine also features the air bearing table, allows for high accuracy, low maintenance wear. We also have the exclusive rotary glass scale in the table. These are all modular machines and are very good solutions for shop floor or lab use. Once eccentricity has been reached on upper and lower levels, the machine will move into measuring position. From here you can see that we do have our high resolution, adjustable force, and limited for notching detector. We also have high accuracy column and ceramic radial arm for accuracy and setting datums in both axes. We also feature a real-time display so you can see the measurement as it takes place to understand what your measurements may look like as it is being measured. We have the ability for R-axis tracking, so as this machine moves forward to take the measurement, as you look between your indicator for your stylus and the motion, you can actually see the R-axis moving to follow to keep your stylus in the center of the range. On the next 300 model, we also have the ability to rotate the stylus to keep it normal to the surface with a motorized CNC head. From here you can see that we are able to rotate and choose a range of degree, keep the stylus normal to the surface. With the CNC motorized head, we're also able to measure in ID, OD, upper face, and lower face. So even if you only have a couple directions, this may be a great solution for you to where your operator does not have to come back and change direction of a probe in order to complete a measurement. It is fully programmable for multiple directions, even if it is only one or two. That way there is less operator interference and quicker measuring cycle times. From here we're taking a flatness trace on the top of the workpiece, and from here we move to the inside and do an ID measurement. The mp4 software comes equipped with the latest standards and settings for form and finish measurements. mp4 also has the ability to find edges of workpieces to form a part coordinate in R or Z axis. From here we will move back to a safe position, load unload position, for the operator to be able to load the next workpiece. Upon completion of our measurement process in the CNC program that we have selected, the report is automatically generated. The reports are fully customizable. You can put your company logo, your measurement information, date, time, what type of measurement cutoffs, whatever you want to use. The information that we had the operator input at the beginning of the program appears here. If we look at some of the measurements that we have performed today, we have our outer diameter cylindricity. We show it here in a 2D plane, also in a 3D plane. We can also at any time adjust this 3D plane to see the optimal view from a three-dimensional standpoint. Also, we have measured the cone roundness. This is when we turn the stylus at an angle normal to our surface. This is our bore ID roundness. Also, we look at our top plane flatness. We can see the flatness and the values there as well. And from here we will also measure coaxiality at a couple different points here and able to do that in the report all at once. Also, from our two traces that we took across the cone, R-axis tracking, we was able to evaluate straightness on both sides of it, and also we was able to compare those two straightnesses for a taper, where we, in this case, we show an included taper of almost 37 degrees. mp4 software is very easy to use. For example, if I had the need, I could come up and pick some different datum points and do a new analysis, a rotary analysis. Maybe I want to do a squareness. I can choose all of my outer diameters, my datum, and I can choose the top face. Next, I choose my point of datum, the outer diameter, okay. And just like that, I have created a new analysis. So once the data is taken, it is easy to add or take away from your report and have the information that you need. Again, if you're looking for a modular system, the Roncom Nex RS300 with a full CNC head is a great solution for multi-directional cylindrical measurements.
Welcome to How To, a Quality Digest series for quality control and quality assurance specialists who need quick instruction on how to get something done. This episode is sponsored by mp4. And in this episode, Craig Howell of CPM Labs is going to show us how to use a SurfTest portable surface roughness tester. Go ahead, Craig.
Correct. This is provided by mp4 to us. It's an SJ210. It has all different kinds of features on it. We have a 2.4-inch display on it. There are a bunch of functions and menu options hidden behind the sliding cover. You have on the back end, you can have a memory slot for an SD card. As it comes, it'll store 10,000 results. It'll store 10 measurement conditions and 1 measurement profile. But for some people, that's just not enough.
It's just not enough.
So it has USB. We've got a USB output. It has SPC output for going right into spreadsheets, that sort of thing. Very versatile instrument. The drive unit itself you can separate from the case, and they have a connecting cable so you can get out about 3 feet away in case the probe has to take a measurement out somewhere and your display just won't fit. You can do it that way. So let's put this all back together again.
So you just detach the drive unit as you show, and you can put that somewhere else in the display. It can be
in a safe place, maybe where no coolant's pouring on it, that sort of thing. Yeah. So in use, one of the first things we would do is we would calibrate it to the standard that mp4 has given us. They supply these in a case with a standard. It's marked at 117-inch RA, which is your basic
micro-inch. Yeah.
Micro-inch. And RA is a type of measurement, an averaging type of measurement. So let's go ahead and turn it on and fire it up and see how it all does. So the first thing we're going to do is to calibrate it to this standard. Whenever you change different stylus, you're going to need to recalibrate. That's not a fault of it, that's just actually how they all go. So we'll go to the menu structure, go to calibrate measurement, we'll choose that one. It says 116.14, that's how this came. The standard they gave us is 117, so we're going to go ahead and modify that. Very simple to do. You just go into a submenu, nominal value. We're going to change the numbers there. Whoops. And change the numbers there to read 117 because that's what our standard is. Pretty simple. Then we're going to store it by hitting the save button. Work our way back out. We are now ready to calibrate. So we're set up on the stand. It's critical that you have the lay of the lines perpendicular to the stylus. That's very critical. You can't just slap it down and hope for the best. You have to pay attention. Push the start button, and we won't want to touch the table or move anything. It's taken its measurements. It'll take a series of 5 different measurements to what we have it set to, and then it will average them, and we'll see how it goes. You'll notice the screen will self-correct when it gets near the edge of the screen one way or the other, which is really nice. So now it's doing its calculation. It had 115.75. We just hit the red update button, and we are now set to 117 for this. So now we are ready to use. It's calibrated to the standard and ready to use.
Okay. So how would we measure an actual part then?
Well, let's go ahead and give a try on one of these jaws that we just happen to have from a different video. And here we're gonna measure right across this.
Now, can you kind of see? You measure. You have to measure across. What you're really wanting to do is measure across the grain. And
correct.
If you hold most parts, you can kind of see the grain on the material, right?
This one's pretty smooth, so I'm suspecting it's not going to be a very high RA. Maybe 10 or 12, somewhere in that range is what I'm suspecting. So we'll give it a try. We'll go ahead, and you can see it. It's not the highs and the peaks and the valleys are not very different. So this isn't nearly like the 117.
Oh, the reference standard, yeah.
So this one, it's doing all the math right now, and it had an RA of 10.
Okay. Now, just out of curiosity, just because I didn't even know metal had a grain, so to speak, until you mentioned it to me. What happens if you rotate that piece 90 degrees and measure it again?
Now you're going to the only thing if you're not perfectly with the grain, you're going to come out of the grain, you might see 2 or 3. You're not going to have
it's
a
going to be much
meaningful
less. Okay,
measurement.
okay, all right.
So that wouldn't have that. They make different types of probes for this. These come out, these pull out. Let me show you how this goes. They pull right out and they're replaceable because they do wear out also.
Sure, they're rubbing across stuff all the time.
And when we calibrate them for customers, we sometimes give them the bad news. They get to buy a new probe because they do wear out. It has so many different math functions on it. It comes with 3 different JIS standards, ISO standards, ANSI, VDA. They have different drive units. Some go transverse. They just move a little bit. It all depends what you're measuring. It could be an O-ring groove that you just don't have a lot of room to work in. So maybe you have to go sideways.
Okay.
So it's a very, very versatile machine. Comes with a carrying case. Let me show you how it works. You can have the actual display unit safely nested in here if you're in a harsh environment. I've already removed the drive unit, so I've removed it from its wire. You can close the display case after you hook up the extension wire. We have an extension wire to go to this drive. So this can be way over in a bad environment. Plugged in through here, through the case. You can get in through the back, or you can get in through the front, either way. You can take your measurement, and then you can just flop this up, and you can see all of your different parameters on here, on the display. So it's just a wonderful tool there.
And I think you'd mentioned to me something, you can also delay it before it starts to take a reading?
That's one of my favorite features. Similar to a timer on a camera, a lot of times you'll be on a very rocky environment where you just can't get it to stay still. As soon as you push the button, it's starting to read and take data. In this case, you can delay it 5 seconds, just like on your camera timer. You can push it, get everything back up, get everything stable, back up. It'll take the measurement, give you a little better consistency.
And about how long will it run on a charge?
It'll take about 1,000 measurements. It all depends on how in-depth the measurements are, how much data it's crunching, but they'll last a long time. We've been working with this all day, and it's been holding up on a 4-hour charge.
All right. Well, Craig, thanks a lot. Thanks to our sponsor, Mitutoyo, for supplying us with the Surf Test Portable Surface Roughness Tester. Thanks to all of you for joining us, and we will see you at the next How To. As the world's largest provider of measurement and inspection solutions, Mitutoyo America Corporation offers a complete selection of machines, sensors, systems, and services with a line encompassing CMMs, vision, form, precision tools and instruments, and metrology data management software. Mitutoyo's nationwide network of metrology centers provides application, calibration, service, repair, and educational programs.
Hello and welcome to this webinar from Taylor Hobson. My name is Mike Mills and I'm the Chief Metrologist at Taylor Hobson. This webinar is one of a series covering basic metrology concepts of form and surface texture relating to our products. In this first webinar, we'll be examining the components of a modern profilometer used for the measurement of surface texture. You should be able to see a question and answer panel on your screen. Please use this panel to type in any questions that you might have during the presentation. I'll try to answer your questions at the end of the presentation. Bear with me a moment. Hopefully you should now be able to see the second slide. Richard, could you just confirm that for me, please?
Yes, we see perfectly. Thank you, Mike. Yeah.
Thanks. Just a little technical difficulty at this end. Okay, so we'll start by asking what a profilometer is in the context of this presentation before looking at the main components of the stylus, gauge and data acquisition system. I won't be covering the whole instrument, and in particular I'll not be covering anything to do with the drive or control systems. I'll only briefly mention surface texture analysis, as this will be covered in a future presentation. During the presentation, I'm going to use some simplified terms and will omit qualifications that would be necessary to make that terminology strictly correct. Hopefully, this will make the presentation easier to follow. Whilst there are different types of profilometer, this presentation will be limited to a stylus profilometer, such as those made by Taylor Hobson. Let's start by defining what I mean by a profilometer. As you probably already know, the word profilometer is simply a contraction of the word profile and the word meter. So a profilometer is a meter for measuring profiles. But what is a profile in this context? Well, there's a definition on the screen, loosely taken from the ISO standards for surface texture. A profile results from the intersection of a measuring plane with the surface of interest so that the measuring plane is at right angles to the surface. For those of you used to measuring surface texture, the plane is usually also oriented to be perpendicular to the main elements of the surface texture, or the lay of the surface. Modern profilometers with their wide range to resolution are often used to measure different properties of the surface, such as form, contour, or surface texture. For the purposes of this presentation, I'm going to restrict the scope to surface texture, and more specifically, I'll be thinking about surface roughness. So a profilometer works by measuring variations in height from a datum. There are two classes of stylus profilometer based on how that datum is implemented. These classes of instruments are referred to as skidded or skidless. With a skidded instrument, the surface itself is used as the datum. A large radius skid rests on the surface and is used to follow the trend of the surface, whilst the stylus measures variations between the surface itself and the skid's vertical position. This arrangement is highly practical and is often reserved for handheld instruments. These instruments are easily adapted to measuring in different orientations on a component that is still mounted on a machining system. The second class of instrument relies on a remote datum, usually embodied somewhere inside the instrument. Using a remote datum also enables measurement of form or contour, provided that there is a sufficiently accurate feedback of the gauging position in the traverse direction. In the ISO standards, skidless instruments are considered as reference instruments. This means that in a situation where there's a difference in a parameter value that has been measured on both instrument types, the value from the skidless instrument takes priority. So this diagram, which is not to scale, is shown purely to facilitate discussion of the concepts involved in skidded measurement. So looking at the instrument in this diagram, we can see how the skid will move over the peaks of the surface. The profile depths will be measured by the stylus, measuring from whatever height the skid rests at. Now, although this drawing is not to scale, an important principle can be seen if we consider measurement of a valley near the current location and in a location to the extreme right of the profile. It's clear that the skid will be at different heights in the two locations. The skidded instrument would therefore measure a smaller valley depth on the right-hand side than a skidless instrument would. In practice, because of the radius of the skid being very large compared to the spacing of the surface of the peaks, the difference in recorded heights should be very small and within the uncertainty of measurement. So this shows a skidless instrument and shows that the gauge is moved in a straight line along a datum surface. The surface under test is usually leveled parallel to the datum prior to measurement. The instrument will now measure the depths of each of the valleys correctly in relation to the highest point on the surface. Here are 3 different profilometers from Taylor Hobson. The Sotronic Duo is an example of a handheld, skidded instrument. This particular instrument is highly versatile as it can be split into 2 parts, allowing the small traverse and data acquisition unit to be located into small places. The Intra and Novus are both examples of skidless systems. The Intra can be used with a range of accessories that facilitate specific measurements. For example, we have a special fixture for the measurement of ball bearings. The Novus is an example of a floor-mounted measuring system. This requires the component to be brought to the system for measurement rather than taking the instrument to the component. This schematic shows the basic building blocks from the stylus tip through to the computer used for analysing the data. Now, there will be differences between different systems that employ different gauging technologies, but I've chosen to represent it this way to highlight some important considerations. These components are the critical path in the measurement of surface texture. One of the key components of the system is the stylus, and often the stylus is interchangeable, such as the one shown here. The stylus can be tailored to a given application by altering the length of the beam or the length of the recess piece to gain access to critical features on the surface of a component. As we shall see later, the length of the shaft will have an impact on the fundamental range and resolution of the instrument. The stylus tip is an essential element forming the contact with the surface under test, and we shall look at this tip in more detail. The size, shape, and the material of the tip will all affect the results. For surface texture, these properties are stipulated in the relevant ISO standards. For fine surface finish, the default stylus is a 2 micron radius, 60-degree diamond conisphere. Other styli are permitted, for example, a 90-degree stylus angle is very common. Stylus radii of 5 micron and 10 micron are also common depending on the roughness values being measured and the industry practice. In many situations, the impact on parameter values due to changing the stylus size will be very small. So what is a conisphere? A conisphere is a cone whose tip has been rounded into a sphere of the appropriate radius. It's the volume of revolution of the figure shown here on the right. Only the spherical part of the tip is used as the measuring surface, and the reasons for this will become clear shortly. The image here shows a 90-degree conisphere tip. The diamond is brazed or bonded into a metallic substrate and ground to a cone whose included angle is slightly smaller than the desired angle. In this case, slightly smaller than 90 degrees. The very last part of the tip is then ground and polished to achieve the required radius and included angle. Because of its small size, it's extremely difficult to image the tip itself, even with a scanning electron microscope. And that's because we're trying to take a profile of a 3D object, which is a cone. The stylus tip affects the data acquisition by providing a mechanical filter on the surface. And this can be seen here in this graphic. Firstly, we can see that the path of the stylus, as recorded by the instrument, tends to broaden the peaks and narrow the valleys. Where there's only a single point of contact between the stylus and the surface, then we can and often do compensate for the stylus filtering effects. Secondly, we can see that where the surface is contacted as 2 points, as shown in the valley of this graphic, there is an area where no information is gathered from the surface. This is shown as the green area here. The true depth of the valley cannot be found. This is a fundamental limit to the measurement process. Now, unlike a linear filter, the filtering effect of the stylus tip is morphological, which means that the degree of filtering is dependent on both the wavelength and the depth of the wave being measured. Another important consideration is stylus flanking. This is where the contact is between the surface and the conical part of the tip. In the area shown on this graphic, as shown as green, no useful information is gathered from the surface. In fact, if this were a truly sharp step, as shown, the system would be measuring the side of the tip rather than measuring the surface. Stylus flanking should be avoided. Where flanking does occur at the end of the measurements, the areas affected can usually be discarded. Stylus tip material. The choice of material is important. Diamond's really good choice for a number of reasons. Firstly, it's extremely hard and so has good wear properties. Nevertheless, we have to remember that it does wear, and so the stylus tip should be checked prior to making any critical measurements. And diamond also tolerates being machined into small features, and so is ideal for making the small radius tips needed for the surface texture measurement. Diamond has a low coefficient of friction, so it slides over the surface easily and causes minimal abrasion. However, it has to be remembered that diamond is brittle and can be easily damaged by shear stresses. This is particularly true of the stylus tip because there is very little material. Remember, it's only a few microns in diameter. The gauge generates an electrical signal in response to the movement of the stylus tip. And there are many different types of gauge that can be used in a stylus profilometer. 3 technologies used by Taylor Hobson are piezo, inductive, and interferometric. Piezo transducers are often used in handheld skidded instruments such as our Sotronic Duo. Inductive gauges can be used either with or without a skid, and these days they're usually used in skidless instruments such as our Form Telesurf Intra and Form Telesurf I-Series products. An inductive system can have switchable gauge ranges, facilitating measurement in different applications. Interferometric systems offer a single resolution available across a wide gauge range. This is particularly useful for measuring form, contour, and surface texture, all in a single operation. Examples of this type of gauge are to be found in our PGI Optics and PGI Novus instruments. The graphic shown here illustrates an inductive gauge. Movement of the stylus tip will cause movement of the armature within the coils of a variable differential transformer. The electronics associated with the transformer produce a signal that is proportional to the displacement of the stylus tip. As can be seen, the stylus is part of a lever mechanism, and hence the length of the stylus beam will affect the range and resolution of the system. In a modern digital instrument, the data acquisition system is responsible for converting the signal from analog to digital. This implies some form of sampling, which is usually triggered either by a timer or some feedback from the Travis unit position. There might also be a need for amplification, especially where there are selectable ranges, such as in our inductive systems. However, there will almost certainly be a filtering stage. Filtering is important for two primary reasons: to reduce or suppress noise, and to ensure that sampling conditions are met by limiting the upper frequencies admitted to the analog to digital conversion stage. If the upper frequencies are not adequately suppressed, then aliasing may occur. This is where a signal is sampled more slowly than necessary, resulting in the sampled signal appearing like a lower frequency signal. This is what we can see in this graphic here, which shows a sine wave in blue that is fast and has been sampled more slowly than required. And you can see the data points that are sampled on there. And when we draw a sine wave through those points, we get the orange sine wave, which is at a much lower frequency. This is aliasing. The attenuation of the filter in the data acquisition system is dependent on the signal frequency. The key question is, where do those frequencies in our signal actually come from? Now, clearly, the signal we're interested in will come from the surface. In surface texture analysis, we're often concerned with the wavelengths on the surface. Now, as the stylus travels over the surface at a constant speed, the gauge signal will contain frequencies that are related to both the surface wavelength and the traverse speed. For a given wavelength, the frequency will increase with the traverse speed, and therefore finer surface finish, which often involves shorter wavelengths, it might be necessary to reduce the traverse speed to record these waves accurately. The frequency resulting from a particular wavelength is calculated by the simple equation shown here, that F equals V over lambda, where F is the frequency in hertz, V is the traverse speed in microns per second, and lambda is the wavelength in microns. Just as an example, if we were to measure a 10 micron wavelength at 250 microns per second, or a quarter of a millimeter per second, then the frequency would be 25 hertz. Increasing the speed to 1000 microns per second, or 1 millimeter per second, would increase the frequency to 100 hertz. Typical cutoff frequencies for the filters in the data acquisition system would be between 200 and 400 hertz. The cutoff frequency is usually a very useful parameter for characterizing filters, but it doesn't tell us the full story of how the filter is going to affect any particular frequency. This is because filters have a roll-off characteristic. Two common roll-off characteristics, the 2CR filter and Gaussian filter, are shown here. As you can see, for both filters, the roll-off is significant, down to about 1/10 of the cutoff frequency. So data analysis is normally provided by a computer system. In a handheld instrument, this might be a microprocessor, or there might be an opportunity to take data from that system to a separate PC. In the larger benchtop systems, it's normally a PC. The data analysis system is responsible for filtering, to select the right bandwidths, and for the parameter calculation. Now, parameters are just numbers that qualify some statistic derived from the data, and those parameter definitions are governed by standards which may be industry standard, national standards, or even international standards. Filtering is used to divide the signal into bands of interest, creating the primary, roughness and waviness profiles from which the parameters are going to be calculated. For primary and roughness analysis, a short wavelength filter, lambda S, or written as LS filter, is applied. The reasoning behind applying the LS filter is to control the bandwidth of the data used in the analysis, to provide comparability between different systems, either from a single supplier or from different suppliers. However, for this to work, the frequencies corresponding to those wavelengths must not be significantly attenuated by the filters in the data acquisition system. Now, we're not going to cover parameters in this presentation. That will be the subject of a future presentation. What is worth noting is that there are many different parameters defined. The parameter definitions are captured in standards, as I've already mentioned. For example, the international standards such as ISO 4287, national standards, industry standards, or even company standards. And I've shown a few on the slide here. Wherever you're making a surface texture measurement, it is important to know which standard you should be using for the calculation. So we've looked at the building blocks of a typical stylus profilometer and some of the different types available. We've seen how the form of the stylus tip can affect the measurement. We've defined flanking and seen how this leads to erroneous data in the measurement. We've considered components of the data acquisition system, in particular filtering. And we've also seen how incorrect sampling can lead to aliasing. We've briefly mentioned data analysis and noted that there are different sets of standards and how it's important to know which standard to use. We've also seen three important areas of filtering in the system. The stylus forms a morphological filter whose response is a function of both the surface wavelength and its amplitude. The data acquisition system will contain some form of filtering, particularly an anti-alias filter. The filter response is a function of the frequency of the signal, which for a given surface wavelength is related to the measurement speed. In data analysis, filters are applied to control the surface wavelength bandwidth and thereby provide comparability of results across systems. These days, there are many filters that we can choose from. However, the filter response is typically a function of the wavelength. We need to take all of these filters into consideration when assessing the measurement process. The stylus form is governed by ISO standards, and there's a recommendation for the choice of stylus size. The filtering in the data acquisition system is outside the control of the user. So the one parameter that a user might be able to control is the measurement speed. On fine surface finish, we might need to slow down the measurement speed to avoid excess filtering. Well, thank you all for your time and attention. Are there any questions?
Well, thank you very much, Mike, for the presentation, and thank you to everybody for attending. Mike, we have a few questions. Are you okay for answering these?
Yes, of course, I can try.
All right, here we go. So first question I've got is from one of the attendees is, what standards do Taylor-Hobson machines use to analyze data? What standards do Taylor-Hobson machines use to analyze data?
So we normally work to the ISO standards. There are many of them. We also incorporate some industry standards. So for example, there are some VDA standards incorporated within the analysis. So the ISO standards, the parameters for the majority of surface finish, standard surface finish, if you like, are covered in ISO 4287. There are some other parameters that are covered in ISO 12085, which is the motif parameter set. And we also support the RK parameter set, which is in the ISO 13565 series. Hope that answers that fully.
Thank you, Mike. Yeah, I've got quite a few questions coming in, so keep going if that's okay.
Okay, yeah.
So the next question I've got is, does ISO recommend use of skidless instruments for research measurements?
Skidless or skidded?
Skidless, it says. So.
Okay, yes, so the ISO recommendation is that you should use a skidless instrument. That's the way I interpret the standards, and the skidless instrument is referred to as a reference type instrument within the ISO standards.
Thank you. Okay, and the next question I've got is, can we measure crankshaft radius? Slightly different question, but
that's a very good question. That's outside of what we're talking about in terms of form. Sorry, in terms of surface texture, because that's going into form measurement. And yes, potentially, because we manufacture form measuring instruments, we can measure the radius of a crankshaft pin or main bearing.
Yeah, thank you. Okay. One more question is, do Taylor Hobson make their own stylie?
The answer to that is yes. We don't make the diamonds. The production of the diamond is a very specialized process, so they're purchased, but the rest of the stylus is made by Taylor Hobson.
Right, thank you. Okay, and I think
it's also worth, sorry Richard to interrupt, it's also worth stating that we offer a design service for special styli for our instruments as well. So we make a number of custom styli for specific applications, and I mentioned that along the way in the presentation.
Thank you. Okay, another question has come in. Is there a lower limit for RA that you would recommend for a 5-micron probe, and a 2-micron probe is required?
So there are recommendations, and they're given in the ISO standards, so I'd refer you back to ISO 4288. I think it is that has that recommendation.
There's a lower limit, yeah, thank you for that. Okay, I think that's all of the questions. Could you say just a little bit about stylus force, the stylus force on the diamond stylus, and what would be recommended?
Yes, of course. The ISO standard for the stylus force, it's stipulated as 750 micronewtons or 75 milligrams, and that's measured at the center part of the gauge range. Okay. The ISO standard also stipulates that there should be a 0 spring constant, so the force should be constant throughout the gauge range. In most cases that's impractical, and there is a small spring involved there, so the stylus force does change throughout the gauge range. That's fairly normal unless you've got a stylus that's held by gravity, for example.
Thank you. And another question come in. How do you inspect a stylus tip prior to use?
That's a very good question. If you're blessed with a scanning electron microscope, that would be one way. Another way of measuring a stylus tip very, very quickly without taking the stylus off the instrument is to use a stylus tip condition standard. There are a number of these that are available on the market, and typically they might be a very sharp triangle with a very small radius. By measuring that triangle, you'll be able to see the curve that you get as the stylus tip goes over the sharp radius. That curve is a combination of both the curve on the tip standard, tip condition standard, and the any deformation in the tip itself. And that's a very, very good way of checking a standard, a stylus, and it's a very practical way of doing it.
Mike, I think that's brought us to the end of our questions. Only to say, there's a new one come in. Let's just have a look. Is there any more detail available about aliasing filters, and is it done by default?
Right, so anti-aliasing is done by default. It's part of a requirement for a data acquisition system. And if you look at any textbook on digital signal processing, you'll be able to find the background information there. If you pop aliasing and digital data acquisition into a search engine, I'm sure you'll come up with lots of articles that explain that.
Thank you. I think that's brought us to the end of our questions, and to say thank you very much to everybody for all the questions and interest, and particularly Mike for your work in preparing this and presenting it. And thank you very much.
Thank you all, and goodbye from me.
Yeah, bye-bye.
Hi, I'm Drew Klaber with Mid-Toy America Corporation. I'm here with Jeremy Banks, and on today's tooltip, we're going to be discussing the difference between skidded and skidless surface finish measurements.
So Drew, many of my customers have questions on when to use skidded versus skidless surface finish.
Right.
So do you think you could take a couple minutes and explain what the difference between the equipment or maybe some different uses that you would have with these devices?
Absolutely, and to start out, before we really get into the difference between skidded and skidless, let's take a look at the components that make up a surface finish gauge.
Okay. So Drew, what equipment do we have here right now?
So I have two units. I have a skidded and a skidless system.
Okay.
These are both made by Mitsui, but these could be, in effect, any brand of surface finish measuring system. All systems are made up of the same components. You have a stylus, and the stylus is the piece that contacts the surface to do the measurement. The stylus feeds into a detector. The detector takes the movement, translates it into a signal that can be measured, and then we have the drive unit, which pulls the stylus and detector assembly back and forth for the measurement. That'll plug into an amplifier, which is where you get your readings from. Now, this is a skidless system, as I mentioned. The skidded system is very similar, except you'll notice that the stylus and the detector are all one piece here. Okay. So I still have the stylus that's protruding out from the detector, but around it is a housing, and that housing is what we refer to as the skid right here.
So what's the purpose of the skid?
The skid is going to act as a mechanical datum for your surface that you're measuring. On a skidless system, that datum is actually inside the drive unit. So you're going to find that most entry-level systems are going to be the skidded unit with the housing around the stylus.
So Drew, now that I understand the physical differences between the devices, what are some differences in application?
Great question. So let's take this pin, for example. That doesn't have to be a pin, it could be any customer application, but it's a piece that somebody needs to measure surface finish on. Okay. As I'm looking at this pin, there's really multiple areas that can be measured. We can measure the top face, we can measure along the axis of the pin, we can measure over the radius. And that's really going to make a difference which unit we use based off what needs to be measured on here.
Okay, well, let's just say I wanted to measure along the axis.
Okay, so if you're measuring along the axis, a skidded unit would be great, because what's important with the skidded unit is that after it makes contact with the part, that the skid is always in complete contact with the surface that's being measured. So if you look at the skid here, there's no gaps between the skid and the part anywhere. It's not sitting at a kind of a weird angle to where the beginning or the end of the skid is off. It's nice, even contact, to where if I were to move the stylus or the skid back and forth, it's always in contact with the part.
And that's important because the skid is the datum, and if the datum isn't making good contact with the part, you get inaccurate measurements, right?
That is correct. So if you were to measure along the axis of this part, you'd be fine. If you wanted to measure the top face of this part, you'd be fine as well.
Okay. Now what if I wanted to measure radially?
That would be an issue with the skidded system. So let's flip the part up here. Now if I were to present the stylus to the area, as I move the stylus back and forth across the part, you notice depending on where I am, either the beginning or the end of the skid are going to be off of the surface that's being measured, right? I'm either going to have a gap at the beginning or gap at the end of the measurement.
Right, and this would be bad because that's the datum and it's not making consistent contact with the part.
That's correct. Now, if I were to take a measurement with this, I could probably spend some time with the setup and actually get a number that's going to show up on my amplifier, but that doesn't mean that the number is a good measurement that I can trust.
Okay, so in an application like this, a skidless system would be better?
That's correct. So you'll notice as I bring a skidless system in for measuring, that by not having a skid, I can actually bring the stylus in contact with the surface. I'm going to get a very good measurement here. You're going to be able to trust these numbers that you're getting from this unit.
So as long as I stay within the stroke of the detector.
That's correct.
Okay.
That's correct. Depending on the unit you have, that will vary how much actual stylus travel you have.
So as long as I stay within my stylus travel, I can measure radially across the part.
That's correct. That would be no issue to actually have the stylus traverse from side to side. Obviously, I'm moving the whole drive unit here, but in an actual measurement process, it would just be the detector moving the stylus.
Drew, that makes sense, measuring round parts versus straight parts. Are there any other features that would lend themselves to a skidless device versus a skidded?
Absolutely. So let's switch parts for a second. And now we're going to take a look at a piston. Notice the piston has a small groove here on the outside diameter. If we wanted to measure this groove, it might be a little difficult to do with a skidded system because as I start to move my stylus in, you notice the skid is larger than the groove that I need to measure. So I could not actually measure the bottom surface of this groove with a skidded unit. However, if I bring my skidless system in, now you'll notice I can easily not only reach the groove that needs to be measured, but I can still have room to measure from side to side along that groove.
So let's say that I have a part with a groove that's a little deeper, or maybe it's a little more narrow. Is there some flexibility in the type of styli that I can use?
Absolutely. With both the skidded and the skidless systems, there are different styli that can be used with that system. So if you need to reach deeper within a part or down within a groove, maybe at a little bit of an angle for a gear tooth, we can accommodate for that.
Okay.
There are more styli options available for skidless systems than there are for skidded systems typically though.
Okay. So other than the physical limitations of the workpiece, is there any other reason that you would use a skidded versus a skidless device?
It's going to come down to what parameters you're measuring. Okay. And when I say parameter, most folks are familiar with terms like RA, RQ, RZ. Those are the parameters that you're actually measuring with the surface finish gauge. Because it starts with the R, it's a roughness parameter. Any gauge, whether it's skidded, skidless, can measure the roughness parameters.
Okay.
If your parameter starts with a W, it's a waviness parameter. We can't actually measure waviness parameters with a skidded unit because the skid itself will mechanically filter out the waveform. So if we're going to look at waviness, WA, WT, or common parameters, we have to start with a skidless system for those measurements.
Okay, great. So Drew, I got to ask, if the skidless system seems a little more versatile, why would someone purchase a skidded system?
Typically, your skidded systems are going to be your entry-level systems.
Okay.
They're going to have a lower price point on the initial system itself. Once you get into the skidless system though, you'll find that the replacement styli are going to be less money than a skidded system because on a skidless, the stylus is a standalone, as to where skidded, the stylus and the detector are both one body, one housing.
Okay, so if I had a simple measurement where I just want to measure a flat piece for an RA, a skidded or a skidless would work either way.
That's correct.
And if I want to start measuring round parts or I want to measure grooves, then I might move into a skidless system.
Exactly, and when in doubt, feel free to give us a call, look us up online. We'd be more than happy to help determine which is the best unit for not only your application, but for your budget as well.
Well, Drew, really appreciate the time today.
My pleasure.
I really helped me out. I think it'll help my customers out as well.
Very good. Thank you guys for watching today's tooltip. If you have any questions or comments, please leave them in the fields below. If you have any suggestions for future tooltips, please let us know that as well.
Also, if someone had some suggestions or some questions about how they're measuring their parts.
Absolutely. Leave them in the comments below. As always, if you have any questions, please feel free to give us a call at 888-MITSUTOYO or look us up online at www.mitsutoyo.com.